Welcome, everybody. So today I'm going to do something different than I normally do. So I'm going to talk about an area that I do a lot of work in called structural equation modeling. This is a very special technique that allows us to test all kinds of models. And then we're going to expand upon it in the next couple of sessions. By the way, there's only 3 sessions left of this course, so make sure you're getting your grand project done. That's your main grading source for this semester. Anyway, so what I'm going to do different is I'm just going to read from my book. So I just recently wrote this chapter on structural equation modeling for my textbook. So I'm going to just talk about it. I mean, I'll read it and then discuss it as we go along. Okay, so it's going to be kind of fun. And then next, I'll show you a little bit about the software, but I'm not going to really deal with that until next session. Okay. And by the way, next session is going to be asynchronous. That means I'm not going to be doing this live. So I'm going to do it asynchronously. All right. That's for Thursday. So let's go ahead and I'm going to start reading. This is kind of fun. I like reading my own work. Statistical methods covered thus far are useful when we postulate simple hypotheses about the relations among variables. More specifically, we have focused on methods in which there is one outcome variable and one or more predictor variables. Some hypotheses, however, involve possibility of more than one outcome variable, and the methods employed to answer these hypotheses are collectively referred to as multivariate methods. Just more than one dependent variable there. The hypotheses involve, for example, the assessment of a measure's factor structure, such as when the researcher designs a new measure. So you're coming in right now. I just wrote a recent chapter on the topic today, and my goal today is to read this and go over this chapter as I'm reading it as well. Okay, so this is my own work here. These hypotheses involve, for instance, the assessment of a measure's factor structure. Just move all this stuff out of the way. Factor structures is when a researcher designs a new measure, for example, a self-concept scale, and seeks to administer it to a sample of participants, and the testing of fit of the theoretical models to the set of data. So structural equation modeling, what we call SEM, is a multivariate method that permits researchers to analyze data to fit a variety of research hypotheses involving one or more outcome variables. So that's kind of what we're doing right there. So you can see this in figure 1 here. You can see it. This is a prototypical example of a structural equation modeling, a structural equation model. And we kind of discussed this a little bit in dealing with exploratory factor analysis, but in SEM, structural equation modeling, circles represent latent variables or factors. These are unmeasured variables. And then you have these squares or rectangles representing what we call measured variables. So this is an example of perhaps a survey that has 9 items with variable 1 through variable 9. And then we have 3 separate factors that are supposed to be underlying or being responsible for why we see variations in these factors. By the way, what's different here from well, yeah, what's different here from what we saw with exploratory factor analysis is you'll notice that each factor is involved with only 3 variables here, right? So factor 1 is related to these 3 variables, factor 2 to these 3 variables, and factor 3 to these variables. When we did exploratory factor analysis, all factors were related to all variables, but some were more strongly related to some than others. All right. So some are more strongly related to some and others. We also have these, again, we have these little error terms here. So these factors aren't going to be perfectly predicting our outcomes. So there's going to be some residual, some leftover here. And anytime you're making any kind of predictor, there's residual. Okay. So that's why you see that even when there's F1 is predicting F2 here, there's some leftover. And this is the residual, the leftover, because you can't make a perfect prediction even from the factor. So it's cool if factors can make predictions. So this is kind of a very, very interesting way of looking at the world. So I can test all kinds of cool hypotheses. I already talked about this. I've already talked about this. Okay, so I said figure 1 includes several arrows. These arrows indicate the nature of the proposed causal pathway, although we cannot determine causation from a simple structural equation modeling, of course, because we need to do an experiment and carefully controlled experiment to do that. This is still some kind of a correlational method, if you will. We can certainly propose causal relations and assess their plausibility using SEM. So you'll notice that, yeah, let me just talk about, go back. Is this figure one? Yeah, I think I rewrote it over here just for simplicity's sake. You'll notice that there are arrows here, and these arrows point from certain factors to other factors. So I'll just introduce a couple of terms here. There's endogenous and exogenous variables. An endogenous variable is a variable that endogenous, I think I wrote it over here somewhere. Yeah, endogenous variable. An endogenous variable is a variable that has an arrow pointing to it, right? So let's see this here, F1 points to F2, right? F1 points to F3. So F3 and F2 are endogenous variables. Variables that have no arrows pointing at them are what we call exogenous variables. So here F2 is an exogenous variable. You could also say R2 is an exogenous variable, as are all these errors, because there's no arrows pointing at them. Okay. Let's see what else. Okay. Okay, most research. So again, I saw somebody else came in now. So this is a chapter that I wrote recently on structural equation modeling. So I'm going to do reading and commenting as I go along. Most researchers employing SEM are interested in the validity of their proposed models. However, they are also interested in testing specific paths for statistical significance. Figure 2 updates figure 1. So this is figure 2 to include pathways. So you can see that there are paths here, like path A, path B, and path C. We can do a lot of things with this. Like I may be interested in which of these pathways is significant. By the way, this can be seen as a confirmatory factor analysis model, but one of the beauties of structural equation modeling is I can actually test hypotheses. Like say, well, I think this causes this, or this has an indirect effect. So say F1 has an affects F2, but indirectly through F3. So I can start doing anything I want. So this is where the beauty of SEM is that we can actually test theoretical models. So I just devise a theory, and then I could say, well, this is, for instance, say something in public health, why some individuals are more likely in some communities to have type 2 diabetes. So I can propose some kind of a pathway that A causes B, B causes C, and I can test this with structural equation modeling. That's something that's not always that easy to do with, say, with regression analysis or other methods. Well, I can do this with regression, sort of, right? I mean, if I have a measured F1 and a measured F3 and a measured F2, I can use a process macro and test for mediation. But these aren't measured variables. See, they're factors, right? They're factors and they have their indicators. So you can't just do that with regression. If I wanted to do this for regression, I'd have to take some kind of a sum of these three, maybe get an average, right? Of these three. And so, but that's already taking away from the complexity of these models because we don't know how strongly F1 is related to V1, V2, and V3. And that's not taken into account if we just add things up in a linear fashion. Okay. It's really, really cool stuff. Well, I can also divide my models. I love doing this. I'm glad I'm doing this. It's kind of fun. I love it. I can also divide my model into what's called a structural model and a measurement model. So here's an example of a measurement model. So the structural model includes proposed relations among the different factors or the different variables, right? Here, I'm just this is what we would call a prototypical confirmatory factor analysis model. So let's say last week when we talked about exploratory factor analysis, I did exploratory factor analysis and I found that F1, whatever that factor is, represents these three variables or is best represented by these three variables. Factor 2 is best represented by these three variables and factor 3 is best represented by these three variables. So remember in EFA, I'll do this whole process where I have my variables and I try to identify how many factors there are or latent variables or underlying variables there are based on the data, looking at the factor loadings, and then say, okay, well, F1 these three factors load on F1, these three on F2, and these three on F3. Okay, so then I'm done with that. I go and then run a confirmatory factor analysis model. So this is your prototypical confirmatory factor analysis model. But what you'll notice here is all the arrows are two-headed, right? They're not pointing in any one direction. So this just says that we assume that they're correlated. This is what we call a measurement model. Okay, measurement model. This is before we go to the structural model. The structural model would be the model where we actually, here, I'll show you here, back here, the model where we actually propose the nature of the relations. Like here we say F1 is a causal factor of F2 and directly and indirectly through F3, right? So this is what we call a structural model. So they are different. The measurement model, and we're going to get into model fit in a second. The measurement model will fit the data far better than the structural model because we're not imposing any great restrictions. We're just saying, hey, there's three factors here and they're just correlated, which is probably likely to occur because we just designed this measure. But in this case, we're imposing very strict restrictions here. So this isn't going to fit the data. We'll talk about that in a second as well. All right. Let's see, returning to path 2, the path coefficients are equivalent to regression coefficients relating predictors, right? Relating predictor variables to outcome variables. For instance, there are two ways you can predict F2. We saw that, right? From F1, a direct pathway, which was indicated by the path A, and an indirect pathway. The indirect pathway, and go back here for a second, the indirect pathway would always be a product term here, right? So this is the direct pathway, path A. The indirect pathway will be path B times path C, right? So that's what I meant by that. I said there's a product of two different things. So we can use SEM to assess possible mediated relations between variables. More on that later. However, before we concern ourselves with the significance of specific path coefficients, our first aim is to assess the validity of our models. There's the fun part. To do so, we compare the data variance-covariance matrix to the variance and covariance matrix generated by our model. This is done using what we call a chi-square difference test. Using a statistical computer package like, say, Mplus, which I asked you all to download. If you didn't, you should download it. There's a free version that will allow us to do what we need to do, but you have to download it on your personal computers. Unless you want to do it here, you have to get permission from IT because they're very strict about what they'll allow to download. Okay, yeah, so I said that, yeah. Well, I'll show you how this is all done in a second. To understand this process, I'll start with a simple example that we can do by hand. So this is going to be fun. And if you like math, don't like math, you might not like this part, but it's not going to be horrible math, but I promise you it'll be something that's worthwhile. We'll use correlations instead of, so a variance covariance matrix is just a matrix. If you recall, a matrix is like a way of organizing data from a number of variables, right? So like if we have two variables, we could have and levels on this in each of those variables, two levels. Let me see if I can show you. Well, I'm going to show you what a matrix is in a second. I mean, anything could be a matrix. That's a matrix too, right? But let's say we have two variables, right? And then each variable has a variance. I'm going to put that here. And there's that's a variance of A and variance for variable B. And then they have a covariance. Like a covariance is a non-standardized correlation. B, and then here A, B. So this is like a 2x2 matrix, right? On the diagonals, you have the variances of each variable. So there's two variables, A and B. You have the variances of each variable, and then on the off diagonal, we have their covariances, right? So that's a standardized covariance is a correlation, right? But what I'm saying here is instead of doing this, I'm going to use correlations because we simplify things. We don't have to worry about the variances. So now our variances become 1. So it just makes it a little easier for us to deal with. And what we have here is the correlations instead of a covariance. That's all I'm saying here. So when using a correlation matrix, the diagonal elements are 1 and the off-diagonal elements are the bivariate correlation. Starting with a simple path diagram, we're going to go to figure 4 and a set of correlations, table 1. We can see how well we replicate the observed correlation matrix. Okay, so the idea is we're going to have a model that we drew, right? We're going to have a model that we drew, and from that model, and we're going to have a correlation matrix. So I have the variables. I ran up correlation matrix. I have the correlation matrix. I have my figure, and I'm going to be able to retrace. Oh, my figure has these path coefficients, and I'm going to be able to retrace from that model. I'm going to trace from that model and create a correlation matrix. And I'm going to see how well that correlation matrix that I created from my model fits the observed data correlation matrix. And that's really, really cool. So just wrap your mind around that for a second. I'm going to take this model and I'm going to be able to test whether it's valid, right? Or is one of many possible valid models, but it's a good model, right? By just comparing it to the observed data. And we're going to use something called Wright's rules. So this is kind of an old school approach, Wright's rules. This is going back to something called path analysis before people started doing structural equation modeling. But Wright's rules for path analysis models. Path analysis, as I said, is a precursor to structural equation modeling with observed variables originally used by geneticists. Sewell writes in his work, there, so it's back in 1934, there are three path tracing rules proposed for estimating correlations from path coefficients. Okay. Rule number 1, there can be no loops. In other words, and I'll show you all this, don't worry. Rule number 1, there can be no loops. In other words, one can only go through a variable once. Rule number 2, no going backwards after going forwards. Rule number 3, one can only use one curved path or one correlation. Another important rule is that we must have at least as many pieces of information as there are elements. We must estimate. Okay, so we're going to have pieces of information. The information we get is the variances and the covariances or the correlation matrix, right? All those are that's the information we have. The things we have to estimate, well, those are things that need to be estimated in our model, like path coefficients, variances, etc. The latter rule relates to model identification. So there's a lot of information here, okay? I gave you those Wright's rules, and now we're talking about model and identification. We're going to obviously have to go through all this. I don't leave anybody without the correct amount of information and the ability to understand this stuff. A model is just identified. So this is a term called just, or a label, just identified, if there are as many pieces of information as there are parameters to estimate. Pieces of information relate to variances and covariances. So equation 1 is used to determine the number of variances and covariances in the model, right? Let's call them covariances for short. So you have n, where n is the number of observed variables, n times n plus 1 divided by 2. So in figure 4, where's figure 4? Here's figure 4, right? 1, 2, 3, 4 variables. That's all I'm looking at right now. I just have 4 variables, right? And let's look at this model for a second. We have BMI, body mass index, and perceived physical appearance. They are assumed to, or hypothesized to predict one's self-esteem directly. See, A and B are direct paths, and indirectly through depression. Okay, so that's what we're looking at. But there's 1, 2, 3, 4 pieces of information here, right? To start with. So based on this model, we have 4 times 5 divided by 2 equals 10. So we have 10 pieces of information. That includes the variances and the covariances. If we go to table 1, which must be on the next page, at table 1, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go, 10 pieces of information. But remember, I'm using a correlation matrix here, okay, just to simplify things. Okay. Oh no, what did I just do? Oh no. Go back to where I was, sorry. I pressed the wrong button there. No back button, right? You don't press the back button. Let's go back. Okay, yeah. It's this button right here. Yeah, I'm an old guy, navigate all this new technology that well. So though we are using correlations, we count it to be 10. Looking at our model, we can count the number of items requiring estimation. So there are 9. So we need 1, 2, 3, 4, 5, 6, 7. What else? Oh, and then the 2 variances here. I didn't have them, but each of these, since since these are exogenous, right, variables, BMI and PPA, they also have variances that we have to estimate. We have here residual variances because these are endogenous variables. Remember I said endogenous means the arrows are pointing towards them. This doesn't include these arrows. This is just a correlation. But arrows pointing at them are endogenous. There's 2 endogenous variables, and then there's these 2 exogenous variables. So here we need to estimate their variances. Okay, so see we have 9 things to estimate. That is really, really good. So we have okay. Thus, given there is one more piece of information than data, we are over-identified. And that's a really good thing. This is important because being just identified doesn't provide flexibility for other theoretical models relating the variables of interest. I mean, you're just testing one model. One thing in science we want is alternatives, especially when we're proposing causation. You don't want to say this is it, because well, this is one of many possible ones, and you want to be able to compare your model to other models. And to do that, you need to be over-identified. In this case, we are over-identified. The worst case would be under-identified, having less information than there are parameters to estimate. In that case, we do not have enough information to solve a model. Okay, so think about that, especially if you're making model adjustments. All right, so here I talk about Mplus for the first time. Mplus is a software package. This software package allows us to test structural equation modelings. I'll be working with that later. I'm not going to, I'll show you some more about it later, but this is because this is part of the textbook. I just, I presented right here. Okay. I ran the SEM in figure 4 using Mplus software version 8.3. I present the Mplus code for the example in figure 5. Yeah, it's interesting that this is like many different packages. It's all syntax related. And here's an example. It's very similar to things that you'd see in other data sets where you have to tell the program where your data are located. And here we use 9999 for missing data. Missing data can be just dots, but sometimes it's better to use numbers, like impossible numbers. Like you're not going to get a 9999 here. Okay, so you'll notice that the data are CSV. So this is comma separated variables. This is something that you get a lot in Excel. You get these comma separate variables. You can download them into Excel really well. For the analysis, I created a data set in SPSS software. So I use SPSS to create them under the variable command. Oh, so just looking at this. So let's look at so here I was just talking about what the program does. So you might as well discuss the program now. So the title statement is not necessary, but if you want a title, you can have a title. So I call it a path model. I provided the location of my data set and what type of data they are. And you notice also we use semicolons here at the end of the statement, which is nice since that's what we use in SAS. The variables, the names and they have to be in order: age, sex, BMI, depression. I just call it the DEPI. I don't know why. Self-esteem, perceived physical appearance. The missing on all these variables is 9999. User variables. So the variables we'll use for this analysis are these 3: depression, self-esteem, and perceived physical appearance. And then I say this is going to be my model. So self-esteem is predicted by perceived physical appearance, depression, and BMI. And then also depression is predicted by perceived physical appearance. So that's basically what I'm doing here. I'm creating this model that we had. And that's exactly what you see in the picture. And then I want some sample statistics in the output. Okay. So here are some output. And really what we want to look at now are a couple of things. We want to look at Well, there's so much different output here, but really what we want to look at is this chi-square test, right? This chi-square test. And we see we have 1 degree of freedom because we have, as I mentioned, we had more data than we had, with one more piece of data than we have information we have to solve. And what we're looking for, and it's interesting, what we want to happen, and I'll be talking about this much more. What we want it to happen is we want to see this chi-square test to be non-significant. The chi-square test here tells us that the variance covariance matrix and the matrix that was regenerated from our model are equal. That's the null hypothesis. The alternative is that they're not equal. We'd like to fail to reject the null hypothesis because we'd like to conclude that there's not enough evidence to say that the variance covariance matrix generated from my model is different from the actual data. And in this case, you see my p-value is really large, so it's not different. So that's a good result. And then there's all these other fit statistics here. We can talk about these more shortly. Okay. More stuff. Here's my estimates. So these are your parameter estimates. Okay. You can see which ones are significant, like perceived physical appearance and depression have significant effects on self-esteem, whereas BMI does not. I mean, you think about this as a regression controlling for these two. BMI is not a significant predictor of self-esteem. And I can't judge strength here because these are non-standardized values. These are unstandardized values. And depression on perceived physical appearance is significant. The higher the perceived physical appearance, the lower depression. Correlation between perceived physical appearance and BMI is significant. I get my means, intercepts, variances, and residual variances. Okay, so there's a lot of good stuff here. So you see this is figure 6 and 7. So let's see what we can go. Yeah, so so the primary indicator of fit is the chi-square test, right? The chi-square test for model fit. There are some people who are very strict adherents to just the chi-square test. And if there's any misfit, you have to actually look for it and explain why you have misfit. So if this was significant, that would indicate that there's some model misfit somewhere in the in my model from between the model and the data, and I'd have to investigate that. We didn't have any here. However, it's quite possible that we could. So you'd want to investigate that. Now, one of the issues, and this is very controversial to some, is that the larger the sample size, the more likely you're to find anything that's any difference can become significant, right? So that's a problem. The chi-square test is very sensitive to sample size. Some will argue, well, that's good because the greater the sample size, you're detecting areas of misfit. Others will say that, well, those areas of misfit are not important. That's why you need to investigate them, okay? But because of that, we have other fit indices, like, for instance, the root mean square error of approximation, the comparative fit index, the CFI, the standardized root mean square residual, and each of these has suggested cutoffs. And these are important to know because, when you're doing these analysis and your chi-square isn't significant, you have to explain it. You can say, yeah, but my RMSEA is good, my CFI is good, my SRMR are good. So, you can look at those in our data. I think we saw them here, right? And say, okay, well, these values are okay. This one isn't that good, honestly, right? Well, actually, it is good. Sorry, it's 0. It is good. It is good. I was thinking, I haven't done an SEM in a couple of, in a while. So, and then you can see the CFI. Well, this is too good. It's 1. I mean, that's like too good. So this is obviously a very simple model. This isn't something you'd normally do. But everything looks really good here. So, okay. So we'd say, oh, wow, we did a great job here. I mean, imagine if you did that. It's like a dissertation or something. You'd be really, really happy to get something like that. Okay, so let me take a moment to demonstrate this is like voodoo, demonstrate how to estimate the variances and covariances or correlations from the parameter estimates. Figure 8 presents our model with the standardized path coefficients. I use standardized path coefficients because we're using a correlation matrix here. Using Wright's rules, we'll find the various correlations and complete table 2. We don't have to do anything to find correlation between BMI and PPA right here, since this is a two-headed arrow, which indicates a correlation. So we know that the correlation between BMI and PPA, remember, is our correlation. That's our symbol we use for correlation, is minus 0.173. And by the way, these asterisks tell us that they're statistically significant. So if I was publishing this paper, I'd want to have asterisks, and I'd want to label significant at, say, 0.05 or 0.01, or sometimes I make two of them if there's 0.01, 3 for 0.0001. Okay? So the correlation between depression and self-esteem is a little bit different. Okay, so actually let's see where's table 2. Where did I put table 2? Let me see. Might be over here. Here's table 2. So first thing I did was that minus 0.17, that's BMI and PPA. So I'm just completing. I'm just filling these in based on my calculations. Okay, so that's the first one I filled in. All right, let's go back. All right. Okay, this for the correlation between depression and self-esteem. So these two right here. So I can get here in two different ways using Wright's rules. I can go from depression directly to self-esteem, and that value is minus 0.534, right? Minus 0.534. I have a second pathway I can use. Remember, one of Wright's rules was you cannot go forward and then backwards, right? But I can go backwards and then forwards. So this is another path I have that relates depression to self-esteem. So imagine I'm trying to drive and there's an accident on this route right here. Darn it, I can't go straight because this would take me 2 minutes to get there. Instead, I have to find a different way to get to self-esteem. I'm going to backtrack this way and then go this way, right? I can do that because this is Wright's rules permit this, right? But you can't go forward and then backwards. So I can go here and then here. So it's minus 0.446 times 0.355. Minus 0.446 times 0.335. So I add those two together. My third way that does not involve going forward and then backwards is going from depression to PPA. So this is like I just tried this way, but traffic is really bad. But I know because I keep on trying all these different routes that there's another way to get there. Depression to PPA to BMI and then to self-esteem. Backwards and then forward. So it's negative 0.446 times negative 0.173 times 0.012, and that's it right here. All right, so I add all those together and I get negative 0.691 for the correlation. Okay, so then I'll plug that into my matrix. Negative 0.691. Here it is right here. See, check it out. And you should know this, and I've used this data set so many times in my classes. I know this correlation from this data set is always 0.6. Just know that, right? All right, so let's go to the next one. This is fun. I hope you're having a good time because I'm having a blast. For the correlation between PPA and depression, where's PPA and depression? PPA and depression. Okay, so there's this way, right? Well, I think that's the only way, isn't it? Let's see. PPA and depression. Yeah, that's the only way. The reason that's the only way is because look, you think, well, can I go this way? You're going, okay, you're allowed to have one of these paths. We have one going forward. Oh, but I'm going backwards. No, so I can't do that. Well, how about this way? This way forward. Oh, going backwards. Can't do that either. So there's only one rule that permits us to, without breaking the rules, right? Like to get between PPA and depressions or correlation is minus 0.446. This is fun. Come on, this is fun. You got to admit it. This is fun. I'm having a blast, right? For the correlation between PPA and self-esteem, there are three pathways. PPA and self-esteem. Let's go back. There's a lot of back and forth here. PPA and self-esteem. PPA and self-esteem. Well, okay, I can go directly. It's 0.355. I can go through depression, negative 0.446 times negative 0.345. I can also go this way, negative 0.173 times 0.012. Is that looks like a 1, 2, 3. All right. So that's 3 different ways. Let's make sure that's not maybe mess up somewhere because yeah, 1, 2, 3 different ways. Perfect. All right. For the correlation between BMI and depression, there's only one plausible pathway. Okay, so it's a BMI and depression. So as you see, we have a whole bunch of these that we're going to go through and trace the paths. So we took all these and completed the table. So I used Wright's rules basically to trace the model and recalculate the variance and covariance matrix, or in this case, the correlation matrix, right? All right. For convenience, I've copied table 1 below. Looking at the 2 table element for element, we see quite good fit with the parameters estimated using the maximum likelihood method. This is borne out in the non-significant chi-square. All right, so this is, well, they're not right next to each other. I apologize, but so you can't really see this. So we can see this 0.69 minus 0.45, and you can take, if you can kind of remember those, you'll see minus 0.69 minus 0.44. So we did a darn good job here replicating that model, right? Sweet. There you go. So now you've learned something that's really, really cool that you can actually do, but you don't need to do this by hand. You're going to do this with a computer. Let's review the results of our SEM, looking at figure 7. All pathways are statistically significant, p less than 0.001, except for the direct effect of BMI on to self-esteem. That one was not significant. The significant effects have asterisks in figure A. Okay, one's advantage of having, okay. So standardized values allow us to make comparisons. You should remember this from doing regression analysis. So we can do this. This is also, it also makes interpretation easy, although there are 3 different types of standardization options available in Mplus. So there's 3 of them. You can read about those. I'm not going to discuss all 3 here. I'm using what's called XY standardization. So I take the B value and multiply it by the standard deviation of the, so X and Y, you think about it as the X being the predictor and the Y being the outcome. So if you think about it from the model, the Y has the arrow pointing at it. So looking at the standardized coefficients, the largest effect is the direct effect of depression on self-esteem. So let's go back to that figure. Let's go back to that figure here. Wherever it is, it should be here. Yeah. These are all standardized values. So depression to self-esteem, these are all standardized. So that means I can make direct comparisons, say, oh, what this is the most strong effect we have, right? Because if we forget this negative sign and just look at the absolute value, 0.534 is bigger than everything else. This one's kind of close, right? But really, this is the major effect that we have. Okay, so, but you have to understand that there are different ways to standardize. So, and actually in the program, you would want to read the different, because you get all these options, the different types of standardizations. Okay. And here I show you how I calculated that. Ooh, another question of interest is the nature of the effect of predictor variables on the outcome variable. For instance, we could ask if the effect of perceived physical appearance on self-esteem is direct or is mediated by depression. We can do this in different ways. As you know from an earlier lecture, we can use the Barron and Kenny approach, which is, has its flaws, but again, the reason I taught you about it is because it's so pervasive that you should know it, even though I think it's kind of a little bit on the old-fashioned side now. So we can, of course, use that approach, right? It's called for the lay researcher. Using figure 4 copied here for convenience, we have an indirect effect from, so we see that right here. So we have an indirect effect. We can test, right? From PPA to depression, to self-esteem through depression. Okay, I guess this is discussing the Barron and Kenny approach. Good for you to review it. First, there must be a significant effect from PPA to self-esteem. So this is a review of the Barron and Kenny approach. Second, The effect of from PPA to depression must also be significant. Must also. Third, the effect of depression on self-esteem must be significant. Finally, the direct effect from from PPA to self-esteem must no longer be significant after the inclusion of the mediator depression into the model. A problem with this approach is, although not stated explicitly, is that it assumes normally distributed product D times C along with normally distributed variance. So the variance for that product, okay? If the variance is skewed in either direction, this can affect the significance of the indirect effect. Yes, because if it's skewed and the variance is really large, it's going to affect the denominator of your test statistic, right? So either it could be, you can overinflate the denominator or underinflate it, and then that'll affect, you can lead to type 1 or a type 2 error, right? False positive or false negative results. For instance, the left skewed variance will reduce the size of the standard error, increase the likelihood of a type 1 error. So just basically what I said, okay? Fortunately, to counter this, Mplus provides, so this is very similar to what we do in the process macro, right? Mplus provides for bootstrapping standard errors. We already know a little bit about bootstrapping, creates a sampling distribution from the existing distribution by resampling from the known distribution and then calculates the variances from the bootstrap data. This allows for statistical testing without assuming normality, okay? We would then use the bootstrapped results to calculate the confidence interval. This is basically what you do in the process macro as well, but this is all built into Mplus. Figure 9 presents the Mplus syntax for assessing the indirect effect. So here, let's take a look at that. So the indirect effect I have here, I have model indirect. So that's what's different here, right? Model indirect, and I'm looking for indirect effect from, where's my figure? From PPA to self-esteem, and it'll calculate, well, it'll automatically calculate this effect. I didn't have to, I mean, if I had a lot of indirect effects, I'd have to specify which one I wanted, right? But here there's only one, so that's, I don't really need to specify it, and it'll just calculate it for me, okay? And I also want the confidence interval, and I mentioned it's bootstrap. And I can actually tell it how many bootstrap samples I want. If I, like here, it's sampling with 1,000, I think, oh yeah, I'd mentioned it, bootstrap equals 1,000 here under analysis, the analysis command, which I didn't have originally, but here I have the analysis command. So originally I just did the model, but now I have to add this since I'm doing bootstrap standard errors. I'm on 1,000 replications, but it can be 10,000, you can do whatever you want. Note that the dependent variable is on the left side. Yep, yeah, that's it. Again, I haven't used this in a while, so I have to remember it. Okay, and here's the kind of output I get. Figure 10 presents the results of the bootstrapped analysis with the bootstrap standard errors. Okay, so these are the bootstrap standard errors, right? You get the total effect, the total indirect effect, specific indirect effect, and you can see, you know, they're being tested for significance here, right? So yeah, the results of the bootstrap analysis with the bootstrap standard error. First, notice that the Mplus provides 4 different effects, the total effect, so that's that including the indirect. So the total effect includes the indirect effect, right? Total indirect effect. In the present case, there's only one indirect effect, so the total indirect effect is the same as the specific indirect effect, right? See, specific is the same as the total indirect effect because there's only one. We also get a direct effect from PPA to self-esteem. In this case, the effects are significant, suggesting that we have partial indirect effect. Partial because the direct effect remains significant. The direct effect didn't disappear if you go back to the Barron and Kenny, which it didn't disappear. So we have partial mediation. We don't have full mediation. Full mediation, this effect, the direct effect would have disappeared. So we can calculate the proportion mediated by dividing the indirect effect by the total effect. In this case, we get 0.40. So there's a 40% of the effect we see from the predictor to the outcome, PPA to self-esteem, is channeled through depression. It's beautiful. And to ensure that our effect is truly meaningful, and this is really important, we need for the confidence interval not to include zero. So a confidence interval including zero means that the population includes no effect, no indirect effect, and that we don't want that, right? So that would zero would be within that interval somewhere, so that, or in other words, the interval would cross zero. You can have 90, 95, 99% confidence intervals. So here's the 90, the 95, and the 99. So of course, a larger interval is wider than the smaller intervals. None of them include zero. So see, what I mean crossing zero is, for it to cross zero, the lower value would have to be negative, and none of them are negative. And here you can see the indirect effect. That's what I mean. It has, right, the 90, 95, and 99% confidence intervals. Look, 5% plus 5% is 10, 90%, 2.5 plus 2.5 is 5, 95, and so on. Okay. Pretty cool. So far, I mean, this is cool. I mean, somebody came up with this. It's awesome. All right. All right, since none of the above, we already did that. Okay, there's much more we can do with structural equation modeling. I will leave most of that to you. Well, actually, I'll show you some of it later next week when we get into some novel and different stuff. Ooh, there you go. All right, so let me just show you some stuff for now. So I was going back to my original lecture before. This is from before when I wrote the chapter. So this was different. Didn't I have something I want? Did I erase it? Let's see. I might have erased it. I was just going to run a model. Guess I could just show you what I wanted to run. No, let's see. All right, let's just run some kind of a model. So here's Mplus. So I asked you to download Mplus. So there's a trial version. There's a trial version of Mplus. Let's see if I can go to our class. Go to trial version of Mplus. Today is March, April 6th, right? Or 7th, April 7th. Okay, so I should say week of April 6th. I messed that up. Okay, but here's where you can download the demo. So you'd go to statmodel.com, and at statmodel.com, you have an opportunity to download a demo version. This demo version it does absolutely everything. The only difference is that it only allows you to have 6 dependent variables. So the dependent variables are the measured variables. I think they could be latent as well. Anything that's a dependent variable. No, continuous latent variables and time series analysis too. We can try it and find out. But generally, what that means is the variables that have these would be the dependent variables, right? So like this has 9, so you couldn't run this analysis in the trial version. It's 1, 2, 3, 4, 5, 6, 7, 8, 9 variables, but you could run something simpler, right? Okay, so you want to download this onto your computer. Again, if you download it onto one of our computers, you'd have to get IT, and they probably won't do it unless I ask them to. All right, but it does everything else, and this is great. I mean, look, you can do path analysis, linear regression, exploratory and confirmatory factor analysis. You can do everything, growth modeling. So we're going to use this a couple different times. So you want to make sure you have it. If you were not in this course and not using the demo, I mean, it's not cheap, but it's not the most expensive program there is. I'm not really sure even how much it costs. It's a general description of a pricing. Scared. There it is. 9. It's actually not horrible. You'd want to have probably the combination if you want everything in it, like run multi-level models, etc. But I think they might have student pricing. Let's see. So there's commercial, nonprofit government. So you're probably Mplus version 9 commercial, nonprofit, government, oh, university price. So we get cheaper value. Okay. Is there student price? Oh, there's student price. Check that out. Student pricing, only 350. So that's cool. That's good. And with that, you have to buy a license every year, and you get all the help you can from the creators, Bengt and Linda Muthane. They and their team provide all kinds of really good support. So I mean, I've used this forever, so I like it. Um, all right, so I did have something I wanted to run. I thought I maybe wrote it out there, but I didn't. So this is actually a real version. This is a trial version. So let's see. There's a couple of things I want to do. One thing I like running is just like just a type equals basic. So under analysis, I do type equals basic. I'll just get some basic information about my data set. So here I located my file somewhere on my computer, and it's a CSV file, which you do have access to. You do have this anxiety CSV file, and the names of the variables are sex, Hispanic, tense, on edge, uneasy, restless, nervous, and anxious. I'm just want to do a type basic. I ask for confidence interval and standardized results. And the variables I'm going to use in this analysis are just the tense through anxious, right? So this looks like I'm probably running a confirmatory factor analysis model, right? And then again, I have a title which you don't need, but to run it, it's very similar to what we have in SAS, where you just click a run button. Generally, you run one program at a time. We have one page for one program. I suppose you could have several different programs here, but I usually just keep one because this isn't the same to me as SAS. And I'll hit the run program, and it'll just spit out the output that I'm looking at. So this is some basic data. I have 1,820 individuals. The number of dependent variables is 6. So you could run this one. And that's why I did it. You could run this one with the trial package. The estimator is a maximum likelihood estimator, maximizes the likelihood of replicating my data source. So let's see. Yeah, just some stuff. It shows me my pattern of missing data. This is how many patterns there are. Like one pattern has everybody's present on all variables. Another pattern has people missing the anxious ones. These are different patterns. This pattern 9 has one pattern, one person only did the restless item and nothing else. It shows me how many individuals. So the majority of people have pattern 1, which is really good. Okay. And here's my covariance coverage to show me how much coverage I have. So it's related to the missing data. This looks like this is my covariance matrix. So this is a prototypical covariance matrix. So what the cool thing about it here is that you see that down the diagonal you have variances, and then the rest are the covariances. And you'll notice on the top half we have nothing because again they are the same. And here's the correlation matrix. Unfortunately, one item, they didn't. There's one left over that should be out here, right? It's the correlation matrix. You'll notice that on the diagonal we have ones, and then everywhere else we have correlations. So it just gives us some data. And so I usually use this just to make sure that the model is working. Did I mess up in some way? Sometimes when you change data from say SPSS or something else to Mplus, you might have some weird characters in there. So this is just a way to check to make sure everything turned out okay before I run my CFA model. So here's an example of a CFA model. All right. So this looks just like what we did before. Again, I'm using just tense through anxious. And by the way, all these variables are continuous in nature. Missing all 999. And how I write, oh, this is interesting. Okay. Take that away. So I wrote this model out to be factor 1 is indicated by the variables tense through anxious, right? There's 1, 2, 3, 4, 5, 6, because again, we can do that. We have 6 dependent variables. Okay, so I'm going to test to see if a one factor. So let's say we did our EFA and did my EFA, and I maybe I came up with a scree plot that showed one factor is the best solution. So I'm going to test this out. So this is a new sample, right? We generally do the CFA after the EFA, right? Although I'm not so sure that's really that important anymore. It's too dogmatic. I mean, if I know what something should look like, I should test it right away. Why do I have to do an EFA for it? So it's something I'm thinking about for future papers and stuff. All right, but my output will be confidence intervals, standardized values, and something called mod indices. And this is a really controversial topic, modification indices. So since I made a change, I'm going to press run. It'll tell me, do you want to save your changes? Yes, and it'll run. All right, so here's my output. Here is my output. 1820 values were used. I might lose a value somewhere because there's some missing data. Although one of the nice things about Mplus, it'll use, even if you have missing data, it'll use what data you have and estimate parameters based on whatever data are available. And I really think that's cool. Let's look at their results. Okay, so what I'm really interested in here is the chi-square test. And if you recall, I said one thing we want is the chi-square p-value to indicate non-significance, right? In other words, I would like my model based on the data to replicate my model that's uh, that's based on the model. Replicate, well, the variance covariance matrix from my model to replicate the variance covariance matrix from the data. And clearly here we don't have that. So my p-values minus is 0.0000 is less than 0.00001. So that's not good. I look at some of my RMSCA values are huge. My CFI value is not adequate. It should be at least 0.95. A lot of things are indicating this model stinks. Not a good fit. So what can I do? All right, so let's talk about this a little bit. By the way, here's the different standardizations. This is the XY, and then there's different ones too, depending on what kind of effect you're looking at to predict your outcome are. All right, so what I'm looking at is I'm going to scroll all the way down here. I don't need any of this stuff now because my model's not good enough. And I'm going to go down here. Modification indices. All right. So this tells me what would happen if I did such and such. All right, so one of the things about CFA is that we propose these effects from our factor to our observed variable. You notice that there's one arrow from the factor to the observed variable. However, we don't have like correlations among the residuals, the leftover stuff, right? So if we go back to any of these pictures, like here, you'll see I have arrows pointing from the factors to the variables, right? But I don't have, where's one that has the residuals? I do have one with the residuals. I got to go back to my book. Go back to the book for a second here. Let's go back a couple of pages. So I just want to make sure this is clear. Picture. I need a picture. I need a picture. I should take my camera. Oh my goodness. Oh, here's no, that's that figure. I call those figures because I just took pictures of them. Not this one. Let's go back to one that has the residuals. Here. Okay. So you'll notice that the factor has an arrow to each of the observed variables, right? And as do the errors. So this is the residual. Remember, we're assuming that the relations among these variables are predicted by this factor, right? High commonalities, if you recall from exploratory factor analysis. The leftover that's not predicted by the factor is our error, residual, disturbance, whatever you want to call it. But you'll notice also that there's no correlations among these, right? What the mod indices proposes is that I can improve my model fit if I change this. So this is restricted to be zero. So right now, the correlation between these two is set at zero, but I can relax that and allow this this correlation to be estimated. And that's going to improve my model fit by a lot. I mean, in fact, it says it'll improve the model fit by the chi-square be reduced by 412 points, right? 0.970. If I were to just release the correlation between anxiety and nervousness. Well, you're like, well, of course, anxiety and nervousness, yeah, they're correlated. Why not release them? Okay, wait a minute. I didn't propose that originally, right? So that's kind of a violation of a rule here. This is what we call post hoc model fitting. So this is saying my model sucks, but I can actually make it better if I do this. The rule for this is that you really need a good reason to do that. Well, because, well, it turns out that on that day, such and such happened. There was an avalanche nearby and that caused people to be nervous and anxious. So therefore, they should be, or we need to take that into account. You come up with something, but if you don't have that, you shouldn't do that. And it's frowned upon to do post hoc model fitting. Okay. So you'd really want to have a reason to do so. But let's see what happens if I do it. So we're going to go ahead and release that. Peace. No, there's too many things open. All right, so let's go ahead and release that. Where's my model? Mplus. It's been a while, so where's my model? I can't. It's been so long since I've done this. I can barely remember how to do it. All right, here. So it's an anxious and what is it? Anxious and tense? Was that it? I'm afraid to go back there. I gotta. Oh, anxious and nervous. Anxious and nervous. So, anxious and nervous. All right, so let's go ahead and do that. Okay, so how do I release you say anxious with nervous. So now this is allowing me to test that. Right? This is permitting me to test that. Okay, so let's try that. So let's run. Let's save, yes. Let's see what happened to the model. All right. Wow. So the model improved a lot. It went down, the chi-score went down to 98.207. Okay, it's still not significant, but if you look at my CFI, it's 0.987 now. A lot of these parameters are pretty good, right? I mean, these test statistics are pretty good now. But I did add this, which I may or may not have great justification to do. And we can take a look and see if there are any more that it's telling me, well, if I do on edge and tan, so I can improve my chi-square by 33 point. I can keep on adding these, but you see, this is kind of stupid. Sorry to say that. It's like cheating. You can just keep on doing things to make it good, but your chances of you're going to improve your chi-square value, but you're going to decrease the likelihood that your article is published because people don't like that. That's called post hoc model fitting. But anyway, these models are nested within each other. So something was constrained equals zero, it's released. So that's a nesting of an effect. So what's the story here is, we can test, we can do our confirmatory factor analysis after we do our exploratory factor analysis. Our goal would be to show that it's just as good, right? Or the model that we came up with is adequate. Remember, as I mentioned at the beginning of this is kind of a longer lecture, but if you remember what I mentioned at the beginning of this today, I said that if you look at the exploratory versus the confirmatory, you'll notice the confirmatory has one path only, or set paths from from the factor to very specific variables, but there are no paths going from here to here, here, and here, or here to here, here, and here. In exploratory factor analysis, there are paths everywhere, right? They just are stronger in some directions than others. So I showed you how we actually do the comparison for the chi-square difference test. And we even did an example by hand. We talked about Wright's rules, which could be fun to do. Party trick if you need, so that was fun. Thank you for such a wonderful. So wait, I'm gonna don't go away yet. Any of you who are here, I'm just gonna stop the recording and then I'll talk to you. But this is for people who are gonna be watching this later. Thanks, everybody. So I'm gonna stop the recording right now.